Hi, how are you? I am Mohammed Ezzat from German University in Cairo. This is the research I'm presenting, a general theory for finding the lightest man-made structure using Voronoi and Delaunay. We mean by lightest man-made structure is a structure that under any given amount of materiality will perform better than other available, at least for the research, other available methods. Our process always starts by this. This is the input of our process. We have a cloud of points that present a load case. This is a presumed structure. And we have a load case, and this is the analysis. This is the produced points, cloud points that we will start working on. Our task is to have an understanding of this point. This is the input of our task, and all we do is to understand what this point represents and to produce something optimal out of this stuff. We can do this by a direct and simple interpretation or by a more sophisticated one. We mean by a direct and simple interpretation the centroid model, and the more sophisticated one is what we call the general theory. Actually, the general theory itself is going to be built on the simple, direct centroid model interpretation of this cloud. These are the tools that we are going during our research: Grasshopper and Galapagos. It's an evolutionary optimizer, runs under Galapagos. This will do the heavyweight lifting for getting an optimized version of the structure. The point cloud that we just presented was produced by Manmade. It's a plugin that runs under Grasshopper. The physical accurate product, the one that we claim to be a very light one, is tested, and the optimization itself is done over Karamba. So Manmade is just producing an input, and the optimization is done by Galapagos by the outputs and the feedbacks we get from Karamba. So the product is a physical accurate product. The physical outcome of this procedure will be a Delaunay triangulation and its dual Voronoi diagram. Delaunay triangulation, of course, because it's a triangulation, it has a better chance for more enhanced structural performance than Voronoi diagrams. We will just jump to a simple introduction to what we mean by Delaunay triangulation and its dual Voronoi diagrams. If we have a circle that contains 3 points of the triangulation, this is in a 2D, the 2D definition. This circle cannot contain any other point for the Delaunay triangulation to proceed. The center of these circles will produce the dual Voronoi diagram. So we'll start by the simple point, the simple model. This is the simple model that we will use to interpret the input produced by Manmade. All the simple model task is doing is we have these were the inputs that we have earlier, and all we doing that we classify these points into clusters, into different clusters. It's called centroid because after we cluster and we group these points into different groups, all we do is we get the center or the mean point. The mean of these clusters actually are presented by different stresses, and we get the mean of the stresses, and based on the mean we get the nearest point that represent this mean, and based on that we get these points. After we get these points, we can produce the equivalent Voronoi or Delaunay forms, because this is all that's needed for Voronoi and Delaunay. We just need a set of points, and these set of points in this centroid model are produced by getting the center of the clustered subset of the points cloud. This classification procedure is made by 2 main themes. either a bell-shaped distribution. It's a very simple one computationally, but it have its drawbacks, and we are going to investigate in more depth. And the other one is machine learning classifiers. The reason that we were interested with the machine learning classifiers was because when I tried to implement this clustering theme, I didn't use the bell-shaped distribution. I tried to use another one, which is the Gaussian mixture and EM clustering, but of course without knowing that such clustering exists. These are the three clustering methods underneath the machine learning classifiers. They are defined in the field of machine learning classification. The actual use of these methods will be clarified soon. So in more detail, the first classification method is the bell-shaped classification distribution. It's actually based on a simple equation. And the beauty of this simple equation that it may produce different forms. It may produce something that resembles the skewed distribution or the normal distribution or other unrelated method like this flatness in the crown of the distribution. But it's mostly the maximum value is always 1. And it will always result to infinity because of this 2. It will always be in the positive side. The bell-shaped distribution, these are the parameters of the function A, B, and C. The Galapagos optimizer examines the various combinations of these variables. Based on the various combination of these variables, we will get a new classification, and the Galapagos will keep modifying these variables until we get a structure that is optimal compared to all the other combinations, the previous combination that's maintained by Galapagos. In the machine learning classifiers, the first will be hierarchical agglomerative clustering. It's a data structure. Every point tests for the closest point in its stresses, and actually it should be related somehow to its location, the 3D location. So it tests for its surrounding for the closest point to its stresses, and based on this, they are agglomerated, and this process the point keeps agglomerating to its nearest either point or cluster of points. Until this clustering ends. It's a data structure. It's not optimizable. It just represents a certain behavior, and we can't control it. It's a data structure, and it have different phases, so it may depend on the initialization on the point you start calculating from. The k-means method is a method that depends on clustering all the points in a discrete way. Each point should belong to a cluster, but it can't work by itself. It has to get an initializer. An initializer, it means a guessing. So you should have, for k-means clustering to work, you need to have a cluster defined and a point that represents that cluster. After that, all of the points of the point cloud are tested to belong to any of these centers more. You will find it. So the more common center that you find common to you, it will belong to it. This means a crisp and a sharp belonging to any of these points to all of the centers. After the clustering, the process repeats itself until a convergence. It always converges to some final result. The final one, which is Gaussian mixture and EM clustering, it's a probabilistic form of the k-means clustering. Each of these points have the opportunity to belong to this cluster and another opportunity to belong to this one, so it's fuzzy in nature. Actually, this is the clustering method that why I got attracted to the machine learning classifier from all this. So how all of these classifiers work? Actually, we can have a way to use these classifiers in a way together, jointly together. We can cluster these classifiers into two groups. The first phase optimization, or the first groups, contains the bell-shaped and the hierarchical agglomerative algorithm. These algorithms are used to reduce the number of clusters and the initial optimization guessings that are important for the k-means to work or the Gaussian mixtures to work, because these cannot work without an initial guessing. The bell-shaped function is very simple computationally, and it produces good results, but not always. It depends always on the nature of the load cases that you have to any element. The bell-shaped may be robust for a load case, but not for another. In this case, we will need an extension of another optimization done by k-means or by Gaussian mixtures. In the computational lab, I implemented somehow k-means, but I didn't test it properly. Hierarchical agglomeration can produce number of clusters and initial optimization guessing, but the bell-shaped is better. This one needs computational efforts more than the available in the grasshopper. The last step is to do a chord optimization. So after we reach a form, all of these have its own point. These points will produce the optimal structure produced by Voronoi and Delaunay. We get the utilization value for each of these chords, and we use again the bell-shaped function to reclassify all of these chords and to assign dimensions separately for all of these chords, and then they jointly will produce a final optimized structure. Actually, this chord optimization adds from 2 to 3 times enhancement to the performance of the optimized Delaunay or Voronoi structure. So it's considered as an important phase. And afterwards, when we compare this method to other available methods, we found that this one can merge somehow to some methods available in the market by this technique of chord dimension optimization. So in summary, this is what we have done. We have a load case. This load case have been fed into Manmade, and it produced for us. This is the input for our procedure. This cloud is classified. Is done by the classifiers that we introduced, and then we present each of these zones by a centroid. This centroid will produce a Voronoi or Delaunay form. Using Karamba, after we produce the diagrams, Karamba will calculate the displacement and the utilization of this diagram. Galapagos will get this displacement, and based on the values of this displacement, it will change the parameters, maybe for the bell-shaped function, and the process will keep iterating until we get an optimal structure, and this is the first optimization. This is the data for our understanding of the cloud, and this is the knowledge that we maintain after we get an understanding of the cloud. The second phase is the dimensions optimization of the chords. Each chord will have its own dimensions. The utilization is classified, so each element of these have its own classification, and we apply the bell-shaped diagram to it again. The displacement of the system is measured, and the Galapagos keeps modifying the parameters until we get there. So this is the centroid implementation. It's direct, it's simple, and computationally wise, I can produce the form in very easy way. Each cluster is presented by a center. And the beauty of this centroid method that you can implement it for the more complicated and actually could be more sophisticated method, which is the general theory. General theory states in a very simple way that the clustering that we have We should represent it only by a point. So if we have a cluster like this, it may be not understandable or not comprehensible from our side to represent it by a point. So why not represent it by another thing like a surface, a curve, or a mesh? It's like a question. It imposes. If we presume that we got the optimal understanding of the cloud by the centroid, but why these shapes are like that from this is the general theory. It's that each of these clusters can be represented by different methods, and these are the physical available variations for each of these clusters. This complicated aim can be simplified somehow to in some abstract ways. So we have here the relations that we care about. All of these clusters, each of these clusters will have a relation to its neighbors. These relations can be summarized as a zoom in and a zoom out. So the resolution of this of the analysis of this cloud can variate from a more resolution or a low one, and we will see this in a more clear way. We have different patterns of relations in between this stuff, including for the form of these the forms, the arrangement, and the stresses of each. Then we get a physical consequence upon which we can conclude or predict. When we reach a conclusion or a prediction, we will redefine the relationship, or we call a relation of a relation, which is a classification of these relations. The other constituent will be a language. So this is the zoom in and zoom out scheme that we talked about. This is an optimal centroid form, and this is the representation scheme. We can actually have many optimizations, not just a single optimization for the centroid. That is depending on the variations of the parameters. Using the same clustering, if we lower the number of the clusters, we will get lower number of points. But that adheres somehow to the main scheme of the analysis of our understanding of the point clouds, and a more resolution one with more points. And by doing so, we here have a summary of somehow this is the optimized form. We can summarize somehow areas like these that conclude some data here, and the more detailed ones will interpret some detailed features here. This all is theoretical. And I didn't implement it rigorously. So why is the general theory? General theory is actually more general than the centroid, and it may give us the opportunity to investigate all the possible variations for any structure optimization. For the moment, I use Voronoi and Delaunay, and the main point is to find a way to always transfer the load to other points. Any form in nature can be adopted somehow by the general theory. This was our first implementation for getting a lightweight structure. I called it analogous system. The point cloud that we have earlier is divided by equal-sized cubes, and based on the mean of the stresses in each cube, I produced randomly number of points based on the stresses on each cube. The drawbacks of this one, of course, was the randomness of the produced points, and I didn't investigate very much. But the performance of this system, the drawbacks, it will consume too much material. It may look somehow adhering to actually a behavior in the system, in the point cloud, but it consumes too much material and it's uncontrollable at the point. If we use some of the techniques introduced in the centroid point, it may be enhanced, but comparable to what the centroid point achieved, it like from 5 to 10 times better than this one. This is the general theory, And this is the actions. These are softwares available in the market right now. I investigated in several few days before, and they produce, they pixelate. They have something like the cloud that will be used, and they call it the analysis, the points cloud analysis, and they pixelate it somehow and will use these forms. I will not compare any of these because I don't have enough knowledge to compare these. So these are some of my produced projects. And this is my research. The main research task is to find a model that encapsulates urbanism. Thanks a lot.